We're now going to jump into lesson number 4, and this lesson is all about dependent events. In lesson 3, we investigated independent events, and those were events, as we can recall here,
Let's recall now,
where one event A has no effect on the occurrence of another event B. So events A and B are completely independent. They do not affect the outcome of each other.
Yep.
We introduced the product rule for independent events,
Yep.
and we
If
can
it's
see
a
it here.
compound event,
Yep. And so let's take a look at an example, just to refresh our memory about what independents were. So let's say you simultaneously roll a die, and you spin a spinner with 8 equal sectors, numbered 1 to 8. What's the probability of rolling an even number and spinning an odd number?
So does the die have any effect on the spinner, or does the spinner have any effect on the die? No, they're independent of each other. They don't affect each other's outcome. So we know it's independent. So we can use our probability of A and B equals probability of A times probability of B. So we'll define our events. A is the event of rolling even with the die, and B is the event of spinning odd on your spinner. And so, okay, well, on a standard 6-sided die, there are 3 even numbers on there. So you got a probability of 1/2 for that. And then same thing, if you've got, sectors numbered 1 to 8, then 4 of them are going to be odd. So we got a 1.5 chance there. And then since they are independent, the probability of A and B happening is just a half times a half, or a quarter. Okay. So that's, they're independent events because the occurrence of one does not affect the occurrence of the other. And this is, we want to just refresh your memory on this, because we're now going to look at events where the probability of one event does affect the outcome of the other in a compound event situation. Yeah.
All right, so here we go with basically what dependent events are all about. When the outcome of an event B depends directly on the outcome of another event A, they are said to be dependent. So a conditional probability of B, which we write as the probability of B given A, or the probability of B vertical bar A. This vertical bar right here, you may have seen in other math courses, and this is of course the mathematical symbol for such that.
Yep.
Right?
Yep.
So it's the probability of B such that A is true is basically the probability that B will occur given that A has already occurred.
Yeah, so there's a condition on B.
Yes.
We're finding the probability that B happened on the condition
that
we
happened.
know A definitely already happened.
Yeah. Yep. And those are the types of problems that we're going to see here. We're going to say, oh, okay, so we can't just, if it's a conditional probability, we can't just say the probability of A times and then look at B by itself, because B is dependent on A.
Yeah.
So we need to give some kind of probability that B will happen, but it's a probability that B will happen given that A has already happened, and that's what we mean by dependent events. So yes, we still are using the word and yes, we still do have a multiplication, but this formula, the form of this formula, is different because this isn't just the probability of B anymore.
Yeah.
This is the probability of B given A.
Yeah. So let's just do a really simple example.
Yeah, we'll just do
an easy one.
Conceptual example.
So let's say you want event A to be pulling an ace from a deck of 52.
Okay.
And then let's say you want event B to be pulling a second ace. If you leave the first ace out. Okay. So then, probability of event A, it's the first event. It's not dependent on anything yet.
No.
That's just 4 out of 52. There's 4 aces in the deck of 52 cards.
Yeah.
But assuming that we got that ace, then the probability of getting another one is dependent on getting that ace. So this conditional probability of B, it's no longer 4 out of 52 because we have pulled an ace out successfully.
Yeah. So there's only 3 aces left.
Out of 51. Yeah. So now we're doing 4 out of 52 times 3 out of 51. Yeah. And that's because the outcome of the second event was dependent on the outcome of the first event. And the conditional probability of B, that A has already happened, is now only 3 out of 51, assuming we did get that ace out the first time.
So very often what we're going to see in these problems, and one of the key giveaways, is that we're going to be either drawing cards or we're going to be taking marbles, and we're not going to replace them.
So we're not renewing that probability.
So it's basically without replacement, is that once one option has now been removed, all the probabilities change.
Yeah, and that's why counting cards and playing casino games, that's why it's so challenging, because every time a card is handed out, all the probabilities change.
Exactly.
Yeah.
So here's an example of basically our first example of dependent events. The probability that Mary will go to the University of Toronto is 0.2.
Yeah.
The probability that she will go to another university is 0.5. If Mary goes to U of T, the probability that her partner Taylor will follow her and go to U of T is 0.75. What is the probability that both Mary and Taylor will attend U of T?
So we're being asked to find the compound probability.
Yeah.
We're being asked to find the probability that Mary goes and Taylor goes.
Mm-hmm.
Okay.
Okay. So what we want to do now is we want to set up our event definitions. So A is the event that Mary goes to U of T.
And we've made that first
Yeah.
because if Mary goes, then Taylor will go.
Yeah.
So A is the first event. Mary going is the first
Yes.
event.
B is the event that Taylor goes to U of T. Now you'll notice in this problem, we don't have any information about the probability of Taylor going to U of T alone. We only have information about the probability of Taylor going to U of T given that Mary is going to U of T.
Yep.
Okay,
So we actually don't have this probability.
No, we don't
PB.
know what the probability of B is, and that's okay because we don't need it when we're looking at dependent events.
That's right.
We know the probability of A. It's 0.2.
Yep.
We don't know the probability of B.
No.
But we do know that the probability that Taylor will go to U of T, given that Mary goes to U of T, is 0.75.
Yep.
So now we can say, what's the probability that both Mary and Taylor will attend U of T is the probability of A and B, which equals the probability of A times the probability of B given A.
Note that we don't even need the probability of B.
It never enters into
Never entered into the equation.
Yeah. So here we have a 0.2 probability times the 0.75 probability, and we get 0.15. So there's a 15% chance that they both go to U of T.
Yep.
Example number 3. In your pocket, Miss Hughes, you have a penny, a nickel, and a dime, which isn't much change. But that's what you've got in your pocket.
All right.
Tell me the probability of reaching into your pocket and selecting a dime.
Well, okay. So the probability of selecting a dime, there's one dime and there's 3 coins.
And we'll say that you're wearing mittens so that you can't tell the difference.
I can't tell the difference.
You can't tell the difference between the 3 coins.
All right.
We're going to cut down on your motor skills.
On my sensory perception. Yeah. So it's a 1 in 3 chance of me selecting this dime. Yeah. Now, we've read ahead a little bit. Oh, and Mr. Jackson, we might have misspelled nickel. Oh, it's cute. It's like a pickle. N-I-C-K-L-E.
L-E.
We've read ahead a bit, well, because we wrote the question.
Yeah.
And we know that our next question is going to be, what's the probability of selecting a dime and then a nickel without replacing the dime? So we're going to define both events. A is the event that we select a dime, because that's what we're going to do first.
Yeah.
And then B is the event that we select a nickel. That's what we're going to do second. Mm-hmm. So the probability of A is just 1 over 3.
Yeah. So you reach into your pocket and you select a dime. The probability of that happening is 1 in 3.
Yeah.
Okay. So now that we've set our event definitions, we can say, what's the probability that you reach into your pocket and select a dime and then a nickel without replacing the dime?
Okay, so that's that without replacement we were talking about.
Yes. So this right here, this phrase, without replacing, that's kind of like a dead giveaway. Oh, this is a dependent event.
Yeah.
Because the probability of selecting a nickel
on its own
is 1/3.
Yeah.
But the probability of selecting a nickel once that dime's already gone is different.
It is. There's still 1 nickel, but now there's only 2 coins left in the pocket.
Yeah. So the probability of selecting in the nickel, given that we've already taken out the dime, is 1/2. So it's a 1 in 2 chance.
Yep.
So now we can say, hey, once we've selected the dime, there's only 2 coins left, the nickel and the penny, and we're gonna try and replace that. We're gonna try and pick that nickel. So basically, what we say then is the probability of selecting a nickel and a dime, here, P, A, and B, is equal to the probability of selecting the dime first, then multiplied by the probability of selecting the nickel, given that we've already taken the dime.
You got it.
Okay, so it's 1/3 times 1/2, and we get a 1/6.
Yep.
And notice this would be different. If we ignored this and we replaced the dime, it would be 1/3 times 1/3.
Yeah.
Which is not what we were asking. We were saying, hey, what's the probability of a dime and a nickel, but we're not replacing the dime.
What's interesting is that if you do replace it, then it becomes an independent event.
Yes, of course.
Right?
Yeah.
And so there are times when you're designing your game, if you want them to replace the card and you reshuffle the deck, well, then you're dealing with independent events.
events.
If you don't have them replace the card, you're going to have a lot of dependent calculations on you.
Exactly.
Yep.
Yeah. Which isn't something necessarily to shy away from.
No.
Okay, so the KCI girls hockey team has 8 wingers. 3 of these wingers scored 4 goals or more. 4 or more goals.
Mhm.
If you choose 2 wingers at random, what's the probability of them both being 4+ goal scorers?
All right.
All right, so here are the 8 wingers on the team.
Okay.
Okay, and so we're just going to show this graphically. What's the probability if you choose 2 at random that they're both 4+ goal scorers? Well, here's the 8 wingers, and here are basically our event definitions.
Okay.
So let's say that A is the event of selecting a 4+ goal scorer.
So we reach in, we say, "You girl, you come with us."
Yeah.
That's event A.
Yeah. So so basically that event is selecting a 4+ goal scorer.
Okay.
B then is the event of selecting another 4+ goal scorer. So we're choosing 2 wingers and we want them to both be goal scorers. Well, we're not going to choose a winger and then put her back in the lineup and then have, you know, because basically what we're looking at is that 3 of these girls, these 3 right here, are the 4+ goal scorers. So what we can say is, okay, well, we know that the probability initially of selecting the first is 3 and 8. There's 8 wingers. 3 of them have scored more than 4 goals.
Yeah.
So the probability of selecting, first of all, a 4+ goal scorer is only 3 and 8.
Yeah.
Well, once we've selected her, and then we go to select a second, the probability of selecting a 4+ goal scorer, given that we've already selected the first 4+ goal scorer, is now 2 and 7.
Yeah.
Because once we've selected one of those wingers, there's only 2 of them left.
Yep.
And there's only 7 of the skaters left. So we have 2 4+ goal scorers left out of 7 wingers remaining.
Yep.
And so here we can say, okay, well, the probability of A and B is the probability of A times the probability of B given A.
Yeah.
3/8 times 2/7 is 6 and 56.
Yeah. So assume when you see these questions that you're choosing 2 marbles, or you're choosing 2 wingers at random, or you're choosing 2 of anything, that if they haven't said with replacement, that imagine that it's 2 things. You grab the first one, and then you grab the second one.
And you're not replacing.
And you're not replacing them. And so that will help you set them up when you ask yourself, well, does it make sense that we'd be putting one back before we grab the second one? And if it doesn't, then you're probably dealing with some dependent events.
Okay. So basically, this probability in terms of percentage is about 11%.
Yeah.
All right. So final example for today.
Okay.
Asks a little bit of a different question.
Okay.
So a card is drawn from a standard deck of 52. What's the probability that it's a jack, given that it's a face card?
Okay, so notice here, they're not asking what's the probability it's a jack and it's a face card. Like we're not being asked for the probability of a compound event.
We're being asked for a conditional probability.
Yes.
So if I said to you right now, what's the probability that a randomly drawn card from 52 is a jack?
Well, there's 4 jacks, so I would say the probability of just randomly drawing a jack is 4 out of 52.
And so I'd say, okay, well, let me give you another piece of information.
All right. What do you
so
got?
Let me say, what's the probability that you've got that what the card that I've just drawn is a jack, but I'm going to tell you it's a face card.
Yeah, it's definitely a face card.
Yeah.
But now what's the probability that it's a jack? Well, there's 12 face cards.
Yeah.
And there's 4 of those are jacks. So now I'm modifying my denominator based on the condition.
Yeah. So
given
that it's a face card, the probability it's a jack would be very different.
4 to 12.
Right.
Instead of 4 to 52.
So here's our face cards.
Yep.
Right. Just to recap, A would be the event of a face card. B would be the event of a jack. Now notice that really the probability of A, the probability of B, these things may or may not be given in a question.
Yep.
Right. So here, basically what I'm saying is, well, the probability of a jack, given that it's a face card, is 4 in 12, which is 1/3, and that's it. That is this problem. We're asking for probability of B given A. This right here is basically a really good way of introducing an A part as part of a bigger question. Kind of like, you know, when I'm asking a question, maybe we'll have you find this kind of conditional probability first, and then move on and use this
Use it
conditional probability
to find a
find a
compound.
compound event.
Yeah. So watch carefully in the wording of the question. If you're being asked to find the probability of a compound event, like that A and B happen, or you might just sometimes be asked to find the conditional probability. And then, all you're doing is you're taking into account more information to modify the pool of possible things you're drawing from. Like in this case, we narrowed it down from 52 to 12 based on the condition that it was a faced card. And so, okay, so now it's only 4 to 12 instead of 4 to 52.
And I would say over the years of teaching this course, this is probably, the wording of these dependent event questions is probably one of the things that gets students the most concerned.
Yeah.
Because it's sometimes tricky to tell which probability we're after. The only way to solve that is, of course, practice and by seeing a lot of problems. Right? So these will become, oh, okay, now I understand what they're asking. But you have to have that experience behind you to see the different types of questions.
And when you go straight to that last question, what is the probability that? You can tell right there whether it's going to be compound or something else. Because what's the probability? So P bracket, that it's a jack. So P bracket, and we've defined that as B. Given that, and that's your vertical line, it is a face card. So then that's your A. So, once you've defined your events, then we realize that what we're being asked for, we translate this sentence
into the mathematics.
Into just this right here.
Yeah.
Right? And so, watch out for that. You can tell in that final question whether you're being asked for the compound event or just maybe one part of that conditional probability.